Hey guys, welcome back to chapter 17. We're going to look at another example of an integrated rate law. And all we know so far is first order, so that's the example we're going to work. So here's our problem. Cyclopropane rearranges to form propene. The reaction is a first order reaction and has a measured rate constant of 3.36 times 10 to the negative fifth. If the initial cyclopropane concentration is 0.0445, what is the cyclopropane concentration after 235 seconds? If you guys want to go ahead and challenge yourself and dive into this problem, pause the video. I'll catch you on the other side. All right, so reading back through this, one of the important things I see here is the reaction is first order. So that's one of the things that jumps off the page at me. The other thing I see is I see time. So how am I going to know if I'm dealing with integrated rate law or not integrated rate law? If there's a time piece in here, like in seconds, that's a good indication that it's an integrated rate law. So it's first order, it's integrated here. Oh goodness. Here is our formula. Okay. So like we did before, we're going to take inventory of what we know, see what it is that we're trying to solve for. So just kind of keeping everything together. So we've got concentration at some time t. We've got our rate constant. We've got our time. And then concentration at some time originally. Okay. So let's read back through the problem. Reaction is first order, has a measured rate constant, so that is K, 3.36 times 10 to the negative fifth. And that is 1 over seconds, or seconds to the negative 1. If the initial concentration is 0.0445, so that is the concentration at time 0, the initial. So 0.0445. What is the concentration after 235 seconds? So that's our time piece. Right, so we know 3 of our 4 variables. We just need to solve for concentration of A after that time has ticked by. So now that we have everything organized, let's just plug it into our equation. So negative 3.36 times 10 to the negative fifth, 1 over seconds, times 200 and, I don't know why I put a decimal in there. 235 seconds. All right. Times 235 seconds plus natural log of concentration initially, so 0.0445. All right, so I'm just going to clean up the right-hand side of this equation and plug some stuff into my calculator. So first I'm going to multiply the first 2 numbers together. So I'm just going to carry that negative down. And we've got 3.36 times 10 to the negative fifth times 235. And we get negative 0.00789. Seconds on top, seconds on the bottom, those cancel. We're left with a unitless number. Then I'm going to plug in natural log of 0.0445, and I get negative 3.11. All right, so just one more cleanup before we can take a big jump to solve. So I'm going to add these two numbers together. So negative 0.00789 plus negative 3.11. And I get negative 3.11789. All right, now we need to solve for concentration of A at time t. And what we're going to use is that Euler's log. So Euler to the, this becomes an exponent. Whatever I do to the left side, I also have to do to the right side. So Euler to the negative 3.11. So Euler and natural log are inverses of one another. So that leaves me with just concentration of A at time t. And then I plug this into my calculator. So I find that E, it automatically says, oh, the next thing you put in is an exponent. And I'm going to type in negative 3.11789. And I get a value of 0.442. That is a concentration, so I know the units are molarity. Last thing we're going to ask ourselves is, does this make sense? Oh, I missed the 0. It doesn't make sense. That should have been there. So the last thing we're going to ask ourselves is, does this make sense? So the original concentration was 0.445. After 235 seconds have gone by, the new concentration is 0.0442. So it went down just a little bit, not a lot, but that's okay. It went down. That's what we would expect. So that is your second example for first order integrated rate law. I hope you guys found this helpful.